Good morning. My name is Bellachehab Anass. I'm a PhD student at Telecom Sud Paris. I'm here to talk about nonlinear consensus in metric spaces. The title of my presentation is Gossip in CATk metric spaces. It is a joint work with Jérémie Jakubowicz, who is an associate professor at Telecom Sud Paris. The problem we are addressing here is in the context of distributed sensor networks that we model by an undirected graph. The vertices of the graph represent the sensors or the sensing agents, and the edges of the graph represent communication links between these sensors. At any given time, each sensor stores measurement data. Each sensor V from the vertex set stores a measurement data that we denote by X subscript V T. And this element belongs to some data space that we note M. The global state of the system will note it by capital X subscript T, which is a vector containing all the measurements of all the agents. How is this network synchronized? So each sensor has its own internal clock. There is no global clock for everyone. This clock ticks according to a Poisson process. And the clocks are assumed to be identical and independent from each other. And when the clock of one agent ticks, that agent is able to perform computations or communicate with neighbors and wake up some of his neighbors. What we are trying to do in the consensus problem is we are given an initial state where each agent has his own measurement, and we want to drive everybody to agree on the same value, which is X infinite, which is in the data space. So in the case where the data space is a linear space, an Euclidean space where we can have addition operations, we know a protocol called the Gossip protocol that solves this problem efficiently. What Gossip protocol does is at each step, one agent wakes up. He communicates with one of his neighbors. They communicate their values. They compute the average of their two values, and they do the update. So for example, these two wake up. They do this update. And if you keep on averaging, you keep doing this operation, hopefully at some point, all the data will cluster around a single value, which will be the consensus, X infinite. And indeed, this has been proven in a paper by Xiao and Boyd. The proof relies on the fact that Euclidean gossip at each state performs linear operations on the global state of the system that can be described by this matrix notation, and you can use linear algebra to prove that you can achieve consensus. Now, in the case where our data space is not Euclidean, where we cannot do addition operations, but we can have distances between points. If we are trying to have gossip in metric spaces, there is a natural way to extend this. Instead of using the average value, we compute the geodesic between 2 points and take the midpoint of that geodesic and do the update rule. So these 2 points, and you have this update. And if you keep doing this long enough, hopefully you converge towards a consensus state. The problem with this idea is that in the case of a general metric space, we do not necessarily have the existence of a geodesic between any 2 points. And even if we do, the geodesic is not necessarily unique, so we cannot really define the notion of midpoint clearly. So if you want our intuition to make sense, what we want to do is to restrict the class of metric spaces that we will study, and we'll try to attempt this generalization too. So this is what we will be doing here, essentially choosing a class of metric spaces where we can extend the Gossip algorithm to, which are CATk metric spaces, and then present our result and how it leads to consensus. So first, why are we interested in metrics, in Gossip in metric spaces? Well, because there are many cases of data spaces of practical interest that are not well taken into account by Euclidean setting, like spherical data, projective space, rotations, and phylogenetic trees, which are purely metric spaces. and cubical complex systems, which are used to model reconfigurable systems. So there are, although why some of these cases are special cases of others, you can make a case that there are sufficient examples for us to be interested in metric Gaussian. There are many previous attempts to generalize this, to generalize to non-linear spaces. Many of them have been used in the Riemannian manifold framework. There are a couple of examples here. What we are interested in is a purely metric approach. This is what we have done in our previous work in a special class of metric spaces called CAT0 spaces. Also, the thing is, we will not be able to say something about the consensus point that we will be reaching, the x infinite. The only thing we're interested in is synchronization. We just want to have all the points agree on the same value, and that would be it. So, to introduce the cat kappa spaces, first we introduce the notion of model space. Cat kappa spaces is just a way to extend the notion of curvature or bounded curvature to abstract metric spaces. So, given a real number kappa, we call a model surface M kappa with constant sectional curvature kappa. It depends on the sign. It is, if kappa is strictly negative, it is the hyperbolic space with sectional curvature kappa. If it is 0, then it's the Euclidean space. If it is strictly positive, then it is the sphere, the n-dimensional sphere with sectional curvature kappa. A quick reminder of the notion of what geodesics are in metric spaces. It's just a special types of curves that verify this relationship here. The endpoints of these curves are called its values at 0 and at the end of the interval. Between any two endpoints, there is not necessarily a geodesic. It does not necessarily exist, and even if it does, it's not necessarily unique. But in the case where it is well-defined and unique, we can make this notation here. We can denote it by simply the segment AB, which is an analogy with the usual segment that we know. And the midpoint would simply be the curve evaluated at L/2. So after transporting the notion of segments and midpoints to metric spaces, we can also transport the notion of triangles, which are essentially three curves connected the same way you would connect in Euclidean geometry. So the cat kappa metric condition is a condition on triangles, and it uses the notion of comparison triangle. So what is a comparison triangle? So if you are given a triangle ABC in the metric space M, a comparison triangle, A kappa, B kappa, C kappa, is a triangle that lives on the model surface, M kappa, which has the same length for each edge. So the length of A kappa, B kappa is the same as AB, and so on. They have the same lengths. Now, such a triangle does not necessarily exist always. It exists if kappa is 0 or negative. It always does. If kappa is strictly positive, then any triangle in M does not necessarily have a comparison triangle in the sphere. But it does exist if the perimeter, the sum of the length, is inferior to a certain constant that we will see in the next slide. So cat kappa inequality is a condition that is on triangles. So if you take a triangle ABC and you take its comparison triangle, A kappa, B kappa, C kappa. And if you take any 2 points, X and Y, on opposite edges, and you take their corresponding points, X kappa and Y kappa, then to verify the cat kappa condition, you need that this distance between X and Y be inferior to that between X kappa and Y kappa, whatever the XY points are, and that's how the triangle verifies this inequality. So a cat kappa metric space is a metric space where every pair of points can be joined by one geodesic, and every perimeter with every triangle with perimeter less than this constant here, in the case of kappa strictly positive, must satisfy this condition yes. And this is the class of space that we'll try to generalize the algorithm on. So a recap of the assumptions. So what we'll be doing is studying a discrete time algorithm. The events, the discrete events are when one agent wakes up and wakes one of his neighbors. At each time, each agent has a value, a measurement value, which belongs to a CATk metric space M. And the two agents are chosen randomly according to a probability distribution. If they have a link between them, a communication link, then the probability is non-zero. If they do not have a link between them, then the link will never be chosen. And the algorithm is essentially just like the average in gossip, and you just keep doing the midpoints at each stage. So what we have previously done in the case where kappa is equal to 0, we have proven that we have consensus with probability 1. The algorithm has a meaning because in cat 0 spaces, between any 2 points, there is a unique geodesic, so you can always define the midpoint. And we have proven that the convergence is exponentially fast. It converges at a linear rate. The function we use to describe the speed of convergence is the variance function. It is the sum of distances between the values. When this function is 0, everybody is on the same value. And what we have proven is that the expected value of the variance is bounded by a decreasing exponential. Now, what happens when kappa is strictly positive? In the case of positive curvature, for example, if you take the sphere and you take two antipodal points, there are many geodesics between them, and you can have an infinite number of midpoints. Like, even if you, for example, choose randomly one of them, in this case, we have one section of the sphere, which is a circle. And if you keep averaging, for example, you are in this state and you choose, for example, randomly one, and you keep doing this, it's not clear that the variance function will decrease. Now, in the case of the circle, it has been proven that you can achieve global convergence. If you just wait enough, there will be a series of fortunate accidents that will bring them all in the same hemisphere. But it's not clear, it's not trivial how this can be generalized to any arbitrary metric space where the curvature is not necessarily uniform. And so what we have done is essentially put even more restrictions in the case of positive curvature. We're putting restriction on the initial values. We're forcing them to be the biggest distance between any two initial values must be inferior to d kappa over 2, which is pi over 2 square root of kappa. And when we make this restriction, geodesics exist and are unique, and you have convexity. So if you start at this condition, you will always remain within it. And so the algorithm is sound. It makes sense to talk about midpoints. And we can prove that it converges to consensus with probability 1. And with linear rate, we just modify the variance function. Instead of sum of distances squared, we make the t kappa of the distances, which is this function over here. This plays the same role as the variance function. If it is 0, then all the distances are 0. We are able to say this because of the restriction. And we have the bound on the expected value of the variance function. Now, how does this work? So at each iteration, we see what happens to the variance function. The variance function is the sum of terms dependent on the pairwise distances. So if at time t, the node vt and node wt are awakened, and what happens is they compute their midpoint and update their values. So what happens is there are 3 terms. There are distances between vt and an arbitrary node that doesn't change, and distance between wt and that arbitrary node, and distances between vt and wt, and distances between nodes that will not change, but these do not influence the variance function. After the iteration, these two collapse, and you only have this 2 times this distance in green. So what is the net balance for the variance function? So you can compute how it has changed after one iteration. It is a term depending on the distance between vt and wt, plus a residual term that you can prove is negative thanks to this inequality here. And if you take the expected value on the 2 sides, you have this proposition that says that the expected value of this increment is inferior to -1 over n the expected value of this expression, which we call the disagreement function. And this disagreement function can be linked to the variance function, using this proposition here, uses the fact that the graph is connected. Combining these two propositions, you have a recursion inequality of this form. And you use this lemma to show that this sequence will be bounded by an exponential, by a decreasing exponential, which will give us the result we want, the exponential of the variance function. So we've done some simulations on spherical data. Here we plot the logarithm of the variance function with respect to the number of iterations. So we have this negatively decreasing slope. That's essentially in accordance with the result that we have. And for the rotation space, so S of t. And again, the same result. The log of the variance of iterations. And so what we have done is we have provided conditions on how we can generalize the gossip algorithm to metric spaces, a specific class of metric spaces called CATk metric spaces. And we have checked that the results are consistent with simulations. What could be done is to see how we can achieve global convergence, how we can relax the initial condition on the initial sets. Yes, if you have this, inequality is this, that L plus L prime plus L second be inferior to this one, to this quantity. So if you have this inequality, then you always have in M kappa, if you take M kappa as your model space, in M kappa you will have a comparison triangle with our initial triangle. That would be. Yes, indeed. This is why we have made the restriction here. We forced them to have, their distances must not surpass this d kappa over 2. This is why we can speak about comparison triangles and about geodesics, which otherwise wouldn't mean much. And essentially, if you try to relax this and have global convergence, it's not trivial how you could do it, but that would be interesting. Yes. Well, yes, there are 3 cases. One where you can essentially, you have a closed form from the geodesic. If you give 2 points, the geodesic has a closed form. You just take the middle. That's a large couple of data sets have this problem. In some cases, particularly in discrete spaces like phylogenetics trees and cubical complexes, there is no closed form, but there are algorithms to compute the geodesic. For example, if you take CATk if you take the reconfigurable system, cubical complexes, and you take 2 points between a cubical complex, there is an algorithm that tells you how to compute this, and then it tells you how to take the midpoint of that geodesic. In that case, it's computationally efficient. It depends on the dimension of your data space. That's the only cases I know where you can compute the midpoint. I haven't come across a case where I don't know how to compute it completely. Um, it, it does. It does work. In fact, it is also interesting. It's just that some cases are just purely metric. You cannot really do additions like phylogenetic trees. It's really not clear how you can add two trees or two configurations in a cubical complex, which is a combinatorial structure. You can't really do that. But in cases like rotation group, yes, you can add them and reproject. It's equivalent to pairwise gossip, actually. It's the same formula. But yes, that works. But there are some cases where you really need intrinsic study, where you're trying to see something that's combinatorial, and there you have only distances. Ah. It's. Mm-hmm. So the thing is, it's not unique. I cannot say much about what it will be. It's just I know that it will be synchronized. The thing about this distributed network is there is no central node. You cannot send all your information to one node and he will process and calculate the Gaussian mean or something. And the nodes essentially, they only know their neighborhood. So they know what their neighbor has. And so it's not, it's a local thing that will eventually become global just by gossiping and propagating. So you can't really tell them to do one instruction and dispatch it to everyone. It's not even, there's not even one single clock for everyone. So that too creates a problem to do this. If you had one central entity, then there would be no need for gossip, essentially.
Even in Euclidean space, you don't get
What?
even in Euclidean space, when I think about something like the Brocard point idea in mind, more than one Brocard, you have subdivisions within the limits of
Yes, yes. Mm. Yes, in the case of this asynchronous. Mm. Yes, it depends on the radius of the sphere. If it is 1, then I think it would be pi by 2, I think.